Cassava roots are not only raw material for livestock, but are also contributing to a green revolution, solving the environmental math problem that the whole world is struggling with. So, what is the environmental problem, and why does it make the whole world struggle to find a solution? In Thailand, the answer does not lie in papers or laboratories, but has been put into actual production and operation: bioplastic beads from cassava starch. This is the northeast region of Thailand, the heart of the cassava processing industry, producing over 50% of processed cassava for the whole country. Cassava is a perennial shrub, growth time from 10 to 12 months, from planting to harvest. With suitable tropical climate and sandy soil, this region reaches an impressive yield of 40 to 50 tons of fresh roots per hectare, an abundant raw material source for the bioplastic industry. The main cassava harvest season takes place from April to June. After 10 to 12 months of growth, roots reach optimal size, full of starch, golden raw material for bioplastic production. Tractors attached with specialized equipment go through the field. Knives cut the parts above ground. Then, hydraulic arms pull the whole root set up. Each plant yields 3 to 8 roots, total weight 4 to 10 pounds. Cassava roots after harvest are processed right at the field. Workers use hands or wooden tools to remove sticking soil, cut off small excess roots, keeping only the main roots. Clean roots are loaded onto farm vehicles or small trucks. Time from harvest to transport must be fast, within 24 to 48 hours, because fresh cassava easily ferments and reduces starch content if left too long. The journey of turning cassava roots into bioplastic begins. Trucks carrying tons of fresh cassava roots leave the fields, heading to modern processing plants. This is when science and technology step in, turning simple agricultural material into high-class polymer material that can replace traditional plastic. Let's explore inside the factory where the magic happens. Welcome to the bioplastic production factory. The first stage is raw material preparation. Fresh cassava roots are poured into the receiving hopper, carried by conveyor belt into the industrial washing system with high-pressure water nozzles and rotating brushes to remove soil, sand, stones. Then, the automated planer cuts roots into thin slices or small chips size 1 to 2 inches to increase contact surface area, helping extract starch more effectively in the next stage. The key stage, separating and refining cassava starch. Cassava chips are ground smoothly in a hammer mill with water creating a paste. This mixture goes through a vibrating sieve and centrifuge to separate fibers, keeping only starch milk, a starch mixture, suspended in water. Then, starch milk goes through a multi-stage centrifuge system at speed 3,000 to 4,000 RPM. Water is separated. High concentration wet starch, 35 to 40%, is collected here. Extraction efficiency reaches 85 to 90%. Wet starch needs to be dried. It is put into a flash dryer or spray dryer at temperatures of 250 to 300 degrees Fahrenheit. Hot air contacts instantly with starch sprayed out in small particles, evaporating water in a few seconds. Dry starch with 10 to 12% moisture falls down, collected by a cyclone. This is pure fine white cassava powder containing over 85% amylopectin, a polysaccharide ideal for producing TPS, thermoplastic starch bioplastic. Starting the magical transformation, plasticizing starch. Dry cassava powder is mixed evenly with plasticizers such as glycerol, sorbitol at a ratio of 20 to 30%, and water about 15 to 20%. This mixture is loaded into an industrial twin-screw mixer, rotating at temperatures of 175 to 200 degrees Fahrenheit for 10 to 15 minutes. Heat and mechanical force break the crystal structure of starch. Plasticizers penetrate molecules, turning hard starch into soft, pliable material. This is the TPS precursor. The hot extrusion stage creating TPS thermoplastic starch. The modified starch mixture is loaded into a giant twin-screw extruder. Inside, temperature from 280 to 320 degrees Fahrenheit and high pressure 1,500 to 2,000 pounds per square inch melts the material completely. Two screw shafts rotating backward at speed 200 to 400 RPM mix evenly and push material through the mold at the output. Molten TPS flows out like ivory white or pale yellow plastic stream, cooling gradually in air or water tank, forming the first polymer strands or sheets. Pure TPS is still not strong enough to make final products. The compound mixing stage is key. TPS is mixed with reinforcing polymers like PLA, polylactic acid, PBAT, polybutylene adipate terephthalate, with a ratio of 50 to 70% TPS and 30 to 50% other polymers, along with mineral fillers like calcium carbonate 5 to 15% and stabilizing additives. This compound mixture goes into a second hot twin screw mixer at 320 to 350 degrees Fahrenheit, creating a polymer blend balancing biodegradation and mechanical strength. Creating bioplastic pellets. The final product. Molten polymer blend is extruded through a mold with many small holes, creating many thin polymer strands. These strands run through a cold water tank, 60 to 70 degrees Fahrenheit, to cool and harden quickly. Then, an automated rotary knife system cuts strands into small cylindrical or spherical pellets, size 2 to 4 millimeters. This is bioplastic pellets. Bioplastic pellets, input material for the bag, box, packaging film manufacturing industry, each hour producing 500 to 800 pounds of pellets. Strict testing ensuring quality. Each batch of bioplastic pellets is sampled randomly sent to the lab. Technicians test tensile strength 15 to 25 megapascals, elongation 100 to 300%, melting point, melting temperature 248 to 320 degrees Fahrenheit. Biodegradation capability. Biodegradation test, according to ASTM D6400 or EN 13432, must decompose 90% within 180 days. And safety for compost. Only pellets fully meeting international standards are certified and packaged. Packaging and preparing for shipment. Standard bioplastic pellets are weighed accurately by automated bagging machines, 55 pounds or 1,100 pounds per bag. PP woven plastic bags or craft paper printed with bioplastic compostable logo, ingredients, storage instructions. Robot stacked bags on export standard pallets, wrapped with protective PE film. Autonomous forklifts move pallets to the finished goods warehouse with temperature and humidity control. Each day, this factory produces over 50 tons of bioplastic pellets. The journey from Thailand to the globe. 40-foot containers containing 20 to 22 tons of bioplastic pellets leave Laem Chabang Port, Bangkok, heading to the US, Europe, Japan. Modern logistics systems with GPS tracking and environmental control ensure pellets do not absorb moisture during 25 to 30 days of sea transport. QR codes on each pallet allow tracing origin from cassava fields to the processing plant 100% transparent. At the destination market, bioplastic pellets are distributed to packaging manufacturing factories. Companies like BioBag, Novolex, or local businesses buy pellets as raw material to blow bioplastic bags, food containers, wrapping films. Film blowing or injection molding machines melt pellets at 300 to 350 degrees Fahrenheit, shaping final products. Supermarkets, organic food stores, restaurants order large quantities. Bioplastic pellet price is 20 to 40% higher than regular plastic, but environmentally friendly. The final consumers, the change makers. Emily, a young mother in Seattle, uses bio bags from cassava to hold food waste for urban compost bins. After 90 to 180 days in an industrial compost environment at 140 to 160 degrees Fahrenheit, the bag decomposes completely into CO2, water and biomass, leaving no toxins. Or the Green Kitchen restaurant in Amsterdam, serving 500 meals daily using containers from cassava bioplastic, after eating customers put into compost bins instead of trash. A small product, big impact. Global environmental impact is amazing. Every year, the world produces 400 million tons of fossil plastic. 50% is single-use, only 9% is recycled. If 20% switches to bioplastic from cassava, we reduce 80 million tons of fossil plastic, equivalent to reducing 200 million tons of CO2 emissions annually. Furthermore, producing plastic from cassava reduces 60 to 70% greenhouse gases compared to petroleum plastic, uses renewable raw materials annually, and creates income for 500,000 Thai farmers. This is truly a sustainable future. Impressive numbers. The bioplastic industry from cassava in Thailand is currently worth over $2 billion and is expected to grow 15 to 20% annually thanks to single-use plastic ban policies in over 80 countries. In 2024, Thailand exported over 300,000 tons of bioplastic pellets, creating over 40,000 direct jobs from farmers to engineers. Companies like PTTMCC Biochem invested $500 million to expand production. Future? Bioplastic could replace 30 to 40% of traditional plastic by 2035. The journey from cassava roots in Thai soil to bioplastic pellets in your hand is a miracle of science, technology, and commitment to protecting the environment. Each bioplastic pellet not only replaces fossil plastic, but also carries the story of Northeast Thai farmers, advanced polymer technology, and a zero-waste future.